So next we are going to discuss the scattering matrix or the S matrix. And briefly, what the S matrix is the time evolution operator that takes the incoming state to the outgoing state. Now, our incoming state will involve some initial particles, and ideally, these initial particles will have some sort of localization given by some wave packet. But at the same time, we want their momentum to be within a well-defined range. So although ideally, the in state should be given by some, distribution of the initial momentum. Now this is just a normalization factor. I'm not going to go into the normalization because I'm not going to be using it, but I just want to show you the idea. And so there would be a state which would have, so this is kind of the momentum eigenstates, and then there would be some distribution given by a wave function psi A and another wave function psi B. And these psi A and psi B, you can think of them as the Fourier transform of the wave packet of the initial particles, because the initial particles will have some sort of wave packet distribution, and this would be the Fourier transform of it. So for simplification, we'll consider our in state to be the momentum eigenstate. Ka, Kb, ket. This should be our in state. And our out state would be the momentum eigenstate. K1, K2, dot, 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 Kn out. So the probability that given this in state that we'll find the out state will be given by the inner product between the in state and the out state modulus squared, and for normalization we divide by the norm of the in state and the norm of the out state. Now note that we are working in the Heisenberg picture. So we are in the Heisenberg picture. But even though we are in the Heisenberg picture, we are labeling our states in and out according to what time of the physical state it represents. So for example, this is the in state, and this means that this is at some time t going to minus infinity. So although in the Heisenberg picture, the states do not depend on time, we can still label states with time because we can label the operators that create those states, and those operators depend on time. So here, it's an in state because the operator which creates this state is in the far past. Similarly, the out state would be a state which is created by operators in the far future. So we can write the inner product between, say, the out state and the in state to be in this form, and where t goes to infinity, and we can think of them as being the time evolved states from the same Hilbert space, that is the Hilbert space created at the same time with whatever operators we use to create the states, but they are connected by this time evolution operator. This is a little bit subtle. So this state and this state, they're from the Hilbert space created by operators which are at the same time. And what this does is that this just evolves both of them, evolves one to one, this one to the far past and this one to the far future. And it's this matrix or this operator, the limit, t goes to infinity operator of e to the power minus 2i of t. This is the operator that we call the scattering operator or S operator. This is the scattering operator. And these matrix elements, so which are out k1 dot dot kn, sorry, I should use this, and then ka dot dot, sorry, ka kb, this is in, and it's the matrix element of k1 dot dot kn and s of ka and kb. So these matrix elements are called the S matrix elements, or in short, the S matrix. Now, all these amplitudes will involve an amplitude which means nothing will happen. That is, all the particles which are coming in will miss all the target particles. So which means there will be no scattering. So the S matrix will have a part, or the S operator will have a part, which is just the identity operator. And there'll be a part where there will be actual interactions. And that part is denoted IT, and T is called the transfer matrix or the transfer operator. So when we work out the S matrix elements for non-trivial scattering, what we are doing is we are actually figuring out the elements of the transfer matrix. So the elements that we are interested in are these. So that's going to have K1, K2, dot, dot, Kn, I times T, which is the transfer matrix, and then Ka, Kb. Now, because of overall momentum conservation, we know that there would be a factor in this transfer matrix element, which will have the form 2 pi to the power 4, and then a four-dimensional Dirac delta function, which will conserve the overall energy momentum. So the zeroth component of this Dirac delta function is the conservation of energy, and the other three components is going to be the conservation of three momentum. And the matrix element, I times m, which is, so I times m is called the amplitude or the matrix element, will be a function of Ka and Kb, as well as, K1, K2. So this is going to be the general form of the transfer matrix. And what we'll see is that it's the Feynman rules that will give us this amplitude, and then we're going to relate this thing to the cross-section. So the probability density is going to be given by the mod squared of the inner product between the out and the in state. And of course, we should normalize this with the norms of the in state and the out state. So this is the probability density. Now, see that because the numerator is of this form, and it has in it two delta functions. So these delta functions can be written as, so we have a delta function. These are four-dimensional delta functions. And there is a square on these delta functions. So we can write this as 2 pi to the power 8. And then one of the delta functions sets the initial momentum for momentum to the final momentum. And therefore, the second delta function, the argument is 0. Now, we can interpret 2 pi to the power 4, delta 4 of 0, as an integral of the exponential function, but with the 0 momentum over all space and time. And therefore, we can think of it as the volume of space times the length of time in which the experiment is being performed. So similarly, what we can do is that we can look at what the in state is going to be, the norm of the in state, and the norm of the in state is, using the usual commutation relationships. The norm of the in state is going to be 2 to the power pi to the power 6, 2 pi to the power 6, the 2 times the energy of the initial particles times 2 factors of the three-dimensional delta function, and that we can write as 4 times EA, EB, and 2 factors of the volume of space. And similarly, the out state is going to be a product of 2 times the energy of the final particles times a factor of the volume for each of these of the particles. So what we can show is that the P dot, that is the probability density per unit time, is going to be given by 2 pi to the power 4, and then a four-dimensional delta function with, say, Ka plus Kb and minus sum over the final momenta, and then the matrix elements squared divided by 4 times Ea, Eb times V, and then we are going to have the product of each of the final particle, 2 times E times F times V. Now, this is a density. So to make it into probability, we have to sum over all the momentum, so all the momentum modes. But this is in the case where it's discrete, that is V, the volume, is going to be a finite volume. But of course, we will take it to the infinite limit. If we take the infinite limit, then the sum will become an integral, and that integral will have the form of a volume times d cubed k divided by 2 pi cubed, so that this volume and this volume, this has the right dimension. So if you do that, then what we will have is that we were going to have for P dot, the measure, we are going to have The probability for an interval is going to be d 2 pi to the power 4, and then d delta 4 Ka plus Kb minus sum over the final momenta divided by 4 Ea Eb times a volume factor, and then we are going to have m squared mod m squared times. Now here we are writing the volume measure, the momentum measure. So d cubed I, and this goes from I to n, and there's 2 pi cubed, and then 2 of E of Ki.